Okay, so let's just continue for our chapter of thermodynamics of gases. So from the previous video, we stopped at the ratio of specific heat capacity, the ratio of specific heat capacity of one gas molecule at constant pressure to the specific heat capacity of one gas molecule at constant volume. So let's just continue and go through for the other subtopics. So this subtopic we're going to talk about the isothermal and adiabatic changes. So before that, we need to know some of the basic principle. So let's say I have my pistons here. So this is the wall of the pistons. So this will be my ideal gas. So let's say I supply my heat to this system. So we know that the internal energy of the gas will increase. So when the internal energy of the gas increase, so it will eventually collide with the wall of the pistons. So finally, this wall of the piston will move from the initial volume to the final volume. So in this case, we can say that the work done is actually positive, which is work is done by the gas. So, okay, so this is what we call expansion process. Expansion. So as for the compression, so from here we have a piston again. So this is the wall of the pistons. So this will be my ideal gas. So let's say I push my wall of the piston from this initial volume, decrease to my final volume, which is here. So this will be my V2. So what I can conclude that the change in work done is basically is negative. So it means that work is done on the gas. So this is what we call compression, and this is what we call expansion. Alright, so okay, so let's just going through the isothermal process. So isothermal process. So this isothermal process, we know that is the condition of the constant pressure. Not constant pressure, should be constant temperature. So, okay, so this isothermal process consists of two types of process, which is isothermal, isothermal expansion, and another process will be isothermal compression. So since the isothermal process is the condition of constant temperature, so based on the okay, so not alright, so if the temperature is constant, it means that the gas molecule does not the internal energy of the gas molecule internal energy of the gas molecule is actually equals to 0. So I can simplify it, which said that the change in internal energy is actually equals to 0. Since there is no increase in temperature, so the energy gained by the gas molecule is actually equals to 0. So this is the main principle for isothermal process. So, okay. So let's just move on to isothermal expansion. So I have my isothermal expansion. So we have the two information, which is the internal energy of the gas must be 0. And from this expansion, we know that the expansion is positive, which is work is done by the gas. So based on the first law of thermodynamics, we know that Q, which is heat supply, which is equal to the change in internal energy and the change in work done. Sum of change in internal energy and the work done by the gas. Okay, so since our internal energy is equal to 0, and therefore I can conclude that my heat supply is actually equals to the work done by the gas. So heat supplied is equal to the work done by the gas. So from here, I can say that the heat supplied, the total energy of the heat supplied is converted completely to the work done by the gas. So the heat supply is, for example, the heat supply is totally converted to the work done by the gas, which to push the wall of the piston from the initial volume to the final volume. Alright, so this is what we call isothermal expansion. So hence there is no increase in internal energy, and hence the so let me just write it down. So hence the internal energy is equal to 0, and hence the temperature is remain constant. So this is what we call the isothermal expansion. So let's just move on to another process, which is isothermal compression. Isothermal compression. So so for the isothermal process, we know that the internal energy is 0. So as for the compression process, which the work done is negative. So it means that work is done on the gas. So this is the condition for the isothermal compression. So based on the first law of thermodynamics, which is the heat supply equals to the sum of increase in internal energy and the work done. So my work done is negative, and hence my substitution of this work done should be negative value. So since my internal energy is 0, we state from here. So hence my Q is actually equals to negative change in work done, and my change in work done is actually equals to negative Q. So from here, I can conclude that my work done on the gas is actually equals to the heat dissipation to the surroundings. So let's say I have my pistons. So let's say I push my pistons from V1 and decrease to V2. So suppose my gas internal energy of the gas will increase since my work since the volume is decreasing. So since the volume is decreasing and the internal energy of the gas will increase. But from this case, the internal energy of the gas which supposed to be increased, and so in I'm sorry, in this case the internal energy will dissipated as heat to the surroundings. So hence the internal energy of the gas, okay, the change in internal energy of the gas is 0, and hence I can conclude that the temperature of the gas, not the temperature of the gas, the temperature of the system remain constant. So this is what we call the isothermal compression process. Alright, so we have done for two of the process for isothermal process. Okay, so we know that the work done for isothermal, okay, let me just draw it down in case you forget. So this is the graph of PV. So this will be my, so okay, this will be my first expansion process with T1. So as for T2, the expansion process will be higher. This is because my T2 is actually bigger than T1. So okay, so this will be my volume for both different temperature. So my work done is the area under the graph. So the work done, we know that from V1 to V2, V1, and this is the P dV, and since PV is equal to nRT, hence P is equal to nRT over V. So these three are the constants, so nRT can be moved out from the equation. So this is V2, V1, and this is 1 over V dV. So nRT is equal, integration of 1 over V is actually ln V. So this will be my V2, V1, and finally nRT, bracket ln V2 minus V1, ln V1. So let me just write here. So what I get is nR2 ln V2 over V1. So this equation we have discussed from the previous video. Okay, so alright. So we have done for isothermal process. Okay, so let me just erase all this one. So let's just go through for the adiabatic changes. Adiabatic changes. Okay, so what is actually the adiabatic changes? So it's defined as, adiabatic changes is defined as the expansion or compression of an ideal gas without heat entering or leaving the system. So, okay. So adiabatic changes is actually defined as the expansion or compression of an ideal gas without heat entering or leaving the system. So basically adiabatic changes is meant by the heat is not supplied or released from the system to the system or from the system. So this is the definition for adiabatic changes. So basically my Q, which is the heat, is actually equals to 0 for both adiabatic expansion and adiabatic compression. Okay, so let's just go through for adiabatic expansion. So, alright, so let me just observe. Okay, before that, there is something need to be told. Okay, so based on the first law of thermodynamics, which is Q equal to internal energy plus W. So this is adiabatic expansion. So since the work done is positive, okay, since my Q is equals to 0, okay, let me just observe. Did I miss something? Okay. Alright, let's just enter for the adiabatic expansion. There is no basic principle for this part. Okay, so adiabatic expansion. So based on the first law of thermodynamics, so the work done basically is positive since the work is done by the gas. So since my Q is equal to 0, so what I can okay what I can conclude that my work done by the gas is equal to decrease in internal energy. So let me just write down work done by the gas is equal to decrease in internal energy. So basically, so this is my okay. So basically, the when work is done by the gas, which is the wall piston will move from V1 to V2. So okay, so when the work is done by the gas, hence the internal energy of the ideal gas will decrease. So this is meant by the adiabatic expansion. So when the internal energy decrease, and hence the temperature will also decrease. Alright, so this is what we meant by the adiabatic expansion. By saying that when there is no heat supply to the system, which is Q is equal to 0, so I can conclude that my work done by the gas is actually equals to decrease in internal energy. Since the decrease in internal energy, and hence I can conclude that the temperature of the system will decrease since the work since the internal energy of the ideal gas is totally converted to the work done to push the wall of the piston to V1 from V1 to V2. So this is what we meant by adiabatic expansion. So we have done for this. first process. So let's just go through for another process, which is adiabatic compression. So let me just erase all this one first. So let's just go through for adiabatic compression. So basically, the compression, the work done is actually negative, which is the work is done on the gas. So based on the first law of thermodynamics, which is Q is equal to the increase in internal energy and decrease in the work done. So since my Q is 0, so I can conclude that, so this is work done plus. So I can conclude that the work done on the gas is actually equals to the increase in internal energy of the ideal gas. So work done on the gas is equal to increase in internal energy of the gas. So increase in internal energy of the gas, and hence the temperature of the system will also increase. So increase in internal energy and increase in the temperature of the system, and hence no heat is dissipated from the system to the surroundings. So this is what we call adiabatic compression. Alright, so we have done for two process of adiabatic changes. So we're still in the parts of adiabatic changes. Oops, okay. Let me just erase this all. So let me just erase this one so that I have a bigger space. Okay, this one as well. Alright, so let's just talk about the equation of adiabatic changes. Adiabatic changes. So from the normal equation, which the heat exists by saying that the heat entering or leaving the system. So what we have for the three gas law equation, we have PV, which is, I think this is the Boyle's law, and this is the constant. So as for the Charles law, which is okay, let me just think of it. So what will be the Charles law? Okay, so the Charles law is actually, okay, let me just check about it. Okay. Alright, so this is the Boyle's law. Boyle's law. And so Charles' law states that V is directly proportional to T, and hence V over T is equals to constant. So this is Charles' law. Charles' law. And as for the Gay-Lussac's law, what we have basically is the pressure is directly proportional to T, and P over T is equals to our constant. So this is Boyle's law basically is pressure is directly inversely proportional to V. Alright, so this is the normal equation for the gas laws, which the Q actually exists, which the Q will basically entering or leaving the system. As for the adiabatic changes, we know that there is no heat leaving or entering the system. So for the other equation of adiabatic changes, it has its own equation, which is in terms of Boyle's law, we have PV, and this will be the gamma, which is the ratio of Cp to Cv. So this will be our constant. As for the Charles law, so okay, so let me just observe it. As for the Charles law, we have Tv gamma minus 1 C. As for the Gay-Lussac's law, we have P1 minus gamma T gamma. So this is the equation represents for adiabatic changes. It has its both three of them has its own derivation, but the derivation is quite long, so I just skip of that derivation. So this will be the three gas equation for adiabatic changes. So this three gas equation does not represent the Boyle's law, the Charles law, and the Gay-Lussac's law, but it's represent for the equation for adiabatic changes instead of three gas law. So they have a bit different from this all these three gas laws. So that's it for their own equation. Alright, so we have done for the equation. So let's just move on to another part. Okay, let me just erase all this one. Okay. So let's just talk about the graph for adiabatic changes. So I have my PV graph. So as I mentioned, so this will be my temperature, the graph of the isothermal changes, which is this will be T1. Okay, this will be T1 and this will be T2, and my T2 is basically bigger than T1. So this will be my volume 1 and this will be my volume 2. So so we know that both of these two curves represent the isothermal changes. So as for the adiabatic curve, which is the curve of adiabatic graph is basically steeper than the graph of isothermal change. So this represents the isothermal change, and this is isothermal change as well. And this curve will represent the adiabatic change, which the heat does not entering or leaving the system. Okay, so my work done basically is here. So this will be my work done of adiabatic changes, which is from I write it wrongly. So this one shall be V1 and this one shall be V2. So this basically is my work done for adiabatic expansion. So alright, so let's just go through for the work done for adiabatic expansion. So let me just erase this graph. So based on the graph just now, we know that the work done for adiabatic expansion is the integration of V2 between V2 and V1, and this is P dV, of course, since the pressure and the volume of the gas is keep changing. So alright, so based on the one of the equation of adiabatic change, which is almost similar to the Boyle's law, which is P V, and this is to the power of gamma, and this will be our constant. So I just move this volume to the other side. So what I get is basically is K over V gamma. So my P is actually equals to KV negative gamma. So I can directly sub this one to this equation. So V2, V1 is equal to KV negative gamma. So this is dV, and let me just erase this one. Okay, so this one as well. Okay, alright, so since this K is a constant, so I can move this constant out of the integration equation. So this V2, V1 is V to the power of negative gamma dV. So let me just continue it here. And my K, so my integration of this V to the power of negative gamma is basically equals to V negative gamma plus 1 divided by the new power. So this is negative gamma plus 1. So this is the law of the integration, which if the power is added by 1, and this will be added by 1, and the base is the power is the new power of this V. So this will be V2 and this will be V1. So let me arrange it to be more clearly. So this is 1 minus gamma, and this will be our 1 minus gamma. So this is V2, V1. So what I can do is move this gamma out of the equation. So what I get is K over 1 minus gamma. So this, okay. So what I get is the V2, 1 minus gamma, minus V1, 1 minus gamma. So this is how we integrate the V to the power of negative gamma, but the equation does not end yet. So since my K is actually equals to PV to the power of gamma, so I can sub this as, so okay, before that I just sub this K into here. So since this K is belong to V2, so I denote this K as K2 V2, 1 minus gamma. So this K belongs to V1, so what I can do is denote this one as K1 V1, 1 minus gamma. So okay, so before that we need to know that why this K is equal to K1 and K2. So since our P1 V1 gamma is equal to P2 V2, so I can conclude that this K which is here after expand into V2 and V1, and hence I can denote this one as K2 and K1, which is P2 V2 and V2 1 minus gamma. Oops, this one should be gamma, and minus P1 V1, so V1 1 minus gamma. So this one should be brackets, and we're not done yet. And let me just erase this one. Okay, alright, so let me just erase all this one. Oops. Okay, so this one as well. So I just continue it here. So from here is equal 1 over 1 minus gamma. So since V2 based from the law of indices, so this V2 is a dot product of V2 1 minus gamma. So I can say that my V2 is to the power of is equal to the power of gamma plus 1 minus gamma. So what I get for final result is V2. So I can say that this three unknown will finally equals to P2 V2. Since this one is only V2, so this same go with the initial PV, which is P1 V1. Okay, so let me just erase this one. So actually we have done for this equation, but to be seen more clearly, we actually change this gamma in terms of positive. So I just factorize this positive outside, so that not positive, I just factorize this negative outside, so that my gamma can be changed to positive. So my 1 is actually negative. So this will be my P2 V2 minus P1 V1. So if I expand this negative into here, so what I get is actually P1 V1 minus P2 V2. So this is the equation for the work done of adiabatic expansion. So okay, so let me just erase all this one and this one as well. Okay, so as for the further information, so here, so what I can say that, okay, so what I can say is, since my PV, okay, there's a K here, sorry, okay, since my PV is equal to nRT, so what I can do is just change this PV in terms of nRT. So this is gamma minus 1, of course, and this is n. So n is the same for both final and initial volume. So nRT1 minus nRT2. So I can basically factorize this nr, which is the constant. So what I get is the T1 minus T2. So I simplify this one T1 and T2. Basically what I get is delta T. Okay, so we have done for this equation. So this is the final answer of the equation, which is the work done for adiabatic expansion. So as a conclusion, we have three equations that is applicable. As for number one, which is this one, and for number two, we have this one. So as for number three, this will be our final equation. So these three equations are the most important, and it is the only equation for the work done of adiabatic expansion to be applicable. Okay, so we have done for this equation. So let's just move on to the last part. And the last part is actually continue from this equation, which is W equals to NR divided by gamma minus 1 and bracket delta T. So let me just delete this one and let me just rewrite it again. Oops. Okay, let me just erase all this one. Okay, so we stop as here, which is the final equation. So this is the delta T. So this delta T can be either positive and either negative. So in terms of adiabatic expansion, so since the adiabatic expansion is the work done, so change in work done is actually negative, and since the adiabatic expansion, any expansion is the work done is actually positive, which is work is done by the gas. So my internal energy basically is negative, and hence I can conclude that my temperature is also negative. So this is the negative for for this case, which is adiabatic expansion. So since my T is negative, so I just sub this one as negative. So from gamma, from here, okay, so let me just observe for a while, okay. So since my gamma, as we discussed from the previous video, my gamma is actually equals to 1 plus 2 over F. So basically I can substitute this gamma as this one. So NR divided by 1 minus 1 plus 2 over F, and this one is negative delta T, and this one can be cancelled, and 1 minus 1 is actually 0, we know that. So this is the division of 2 over F. If I move it to the upper parts, so what I get is F over 2 NR delta T. Oops, I forgot about the negative. So this is my negative T. So what I get is negative F over 2 NR delta T. So this equation is quite familiar for us, which is, oops, okay, this is the change in work done. So this F over 2 nRT basically is the internal energy of 1 mole of gas. So what I can conclude, what I can say is the work done by the gas is actually equals to the decrease in internal energy. Alright, so this is how we determine the internal energy in terms of decreasing or increasing. So this case is the decrease in internal energy. So what about the uh, the adiabatic compression? So let me just erase all this one again. So this one can be cancelled and this one can be cancelled as well. Okay, so let me just continue from here. So since the adiabatic compression, so my work done is basically equal to positive. Okay, so from here we can say that the temperature is positive because the increase in internal energy will causes the temperature also increase. So how I can prove that the internal energy actually increase? So from here I can say that the increase in temperature, so okay, this one should be, and here we have delta T and 1 minus 1 as well, same as just now. 1 minus 1 is 0 and this one is moved to the upper parts. So what I can get is F over 2 nR delta T. So I can conclude that my internal energy of the ideal gas is actually increasing. So this is how we prove the increase in internal energy of the ideal gas during the adiabatic compression. Alright, I think that's it for this chapter. So we have discussed all the subtopics for this chapter, which is the thermodynamic of gases. So I think we stop here. If there's any question need to be asked, please comment below this video, and I'll see you in next video, which is the revision for this chapter. So I'll see you next time. Okay, thank you. Bye.